Here's a story that actually broke the internet twice and then quietly fell apart under the weight of its own evidence, and almost nobody covered that second part the way they covered the first. If you've spent any time online in the last year, you've probably seen the headline, "James Webb Space Telescope detects signs of life on a distant planet called K2-18b." It sounds like the biggest discovery in the history of science. It's circulated exactly like the biggest discovery in the history of science. And the truth of what actually happened, which unfolded across 3 separate scientific papers between 2023 and January of 2026, is a far more honest, far more interesting story about how real discoveries get made, tested, and sometimes taken apart, piece by the very community that found them. Let's start with the planet itself, because K2-18b earned its reputation long before the word biosignature ever entered the conversation. It sits about 124 light-years away in the constellation Leo, orbiting a red dwarf star, and it is nothing like Earth. It's what astronomers call a sub-Neptune, roughly 2.5 times Earth's diameter, with gravity pulling almost 3 times as hard as ours. It sits inside its star's habitable zone, the region where temperatures could allow liquid water to exist, and it's wrapped in a thick, hydrogen-rich atmosphere. Some scientists, led by Cambridge astronomer Niku Madhusudan, believe K2-18b could be what's called a Hycean world, a planet theorized to be covered by a single continuous global ocean beneath that hydrogen envelope, potentially hundreds of miles deep. That theory alone made K2-18b one of the most closely watched exoplanets in the search for habitability, years before Webb ever pointed at it. Then, in 2023, Webb's early observations picked up something that made headlines even then: faint, low-confidence hints of a molecule called dimethyl sulfide, or DMS. On Earth, DMS is produced almost exclusively by marine life, mostly phytoplankton and algae, releasing it into the ocean and atmosphere. It's one of the molecules astrobiologists have long flagged as a potential biosignature, a chemical fingerprint that, if found somewhere with no other explanation, would be extraordinarily hard to explain without biology. But that first 2023 signal was weak, statistically speaking, sitting at roughly a 2 sigma confidence level. In plain terms, that means there was still about a 5% chance the whole thing was just noise dressed up to look like a pattern. Scientifically, that's nowhere near enough to claim anything. It was, at best, a lead worth chasing. Then came April of 2025, and this is where the story most people actually remember begins. Madhusudan's team returned with new mid-infrared data from Webb's MIRI instrument, and this time they reported a stronger signal, dimethyl sulfide and a related compound called dimethyl disulfide at roughly 3 sigma confidence. That's a meaningfully bigger claim than 2023, translating to something like a 1 in 370 chance of the pattern being a random fluke rather than a real signal. The announcement detonated across global media within hours. Headlines called it the strongest evidence yet for life beyond our solar system. Madhusudan himself was quoted describing it as potentially a transformative moment for the search for life in the universe, while also being careful, in the same breath, to caution that more data and more scrutiny were needed. That caution got lost almost instantly in the retelling. Within days, strongest evidence yet had mutated across headlines and video titles into flat declarations that Webb had found a living planet, an ocean world teeming with alien biology, a fully habitable world confirmed. None of that is what the paper said, but it's what a lot of the internet decided it said. Here's why that gap matters so much, and it's the thread we're going to pull on for the rest of this video. In science, a 3 sigma detection is genuinely exciting, but it is explicitly, deliberately, not a discovery. The gold standard the entire scientific community holds itself to before declaring something real, whether it's a new particle in physics or a biosignature. On an exoplanet is 5 sigma confidence, a threshold so strict it corresponds to roughly a 1 in 3.5 million chance of the result being a coincidence. Madhusudan's own team knew this, their own paper said this, and what happened next, across the following 9 months, is a case study in exactly how science is supposed to work when the stakes are this high. Other teams didn't. Celebrate the announcement, they immediately went back into the same raw Webb data, using different methods, different assumptions, and different statistical frameworks to see if the signal held up. And what they found is the part of this story that almost nobody put in a headline, and it's where we're headed next. Within weeks of the April 2025 announcement, independent teams around the world started pulling apart Madhusudan's data. And this is normal, healthy, necessary science, not some conspiracy to debunk an exciting result. Astronomer Jake Taylor was among the first to publish a reanalysis, and his conclusion was blunt. Using the same publicly available Webb data, he found no statistically significant evidence for dimethyl sulfide at all. Around the same time, a separate team led by Raphael Luque reanalyzed the full dataset spanning 3 different Webb instruments: NIRIS, NIRSpec and MIRI, combining near-infrared and mid-infrared observations that the original April paper hadn't fully incorporated together. Their conclusion, published later in 2025, confirmed methane in K2-18b's atmosphere at a solid 4 sigma level, genuinely real, no argument there, but found no statistically significant evidence for either carbon dioxide or dimethyl sulfide. Luque's team went further, testing whether other, entirely non-biological molecules could explain the same spectral wiggle that had been attributed to DMS. Ethane, a simple hydrocarbon known to exist on planets and moons throughout our own solar system, fit the data just as well. Luque's own comment on the situation was direct. If a mundane, already known molecule like ethane can explain what you're seeing, you don't reach for an exotic biosignature molecule until you've ruled out every boring explanation first. That's not skepticism for its own sake. That's the entire discipline of astrobiology trying to protect itself from crying wolf. Then, in October 2025, came a study from Luis Wellbanks at Arizona State University that dug even deeper into the statistical foundation of the original claim. Wellbanks and his co-authors used what's called an agnostic retrieval approach, essentially, testing the data against a much broader library of possible molecules instead of the narrower, more constrained set the original team had used. Their finding was one of the more damaging blows to the DMS claim. The specific molecular set used in the original detection was so narrow that it significantly shaped and arguably biased what the analysis was even capable of finding. When Wellbanks opened up the possibilities to a wider range of chemistry, the data no longer robustly pointed to DMS at all. It was equally, sometimes better, explained by other compounds with no biological implications whatsoever, in a particularly striking number from a related 2025 analysis, when researchers ran the same K2-18b spectrum through 87.5% of their preferred retrieval configurations. The vast majority simply did not favor the presence of DMS or DMDS in the atmosphere at all. The most decisive blow, though, came from an unexpected direction: NASA itself. In July 2025, a NASA-led team uploaded a new analysis to the Archive preprint server, later accepted for publication in the Astrophysical Journal Letters, that took the most careful, methodical look yet at the full body of evidence. Their conclusion confirmed what K2-18b's fans already knew, that it's a genuinely fascinating, water-rich world with an atmosphere that may be as much as half water by mass, alongside confirmed methane and a complex chemical environment worth continued study. But on the specific question of dimethyl sulfide, the molecule that had generated every headline, the NASA-led analysis found only a tentative signal at roughly 2.7 sigma confidence, essentially back down near where the story started in 2023, and nowhere close to the 5 sigma threshold required to call anything settled. And then, in January of 2026, the story took its most striking turn yet. A new paper from Wellbanks and his collaborators, this time going even further than earlier critiques, concluded that the original dimethyl sulfide detection appears to have been, in the team's own characterization, a false alarm. Not fraud, not incompetence. Nobody involved in this story has been accused of either. Just the ordinary, sometimes humbling process of science correcting itself once enough independent eyes and enough independent methods get applied to a genuinely difficult measurement. Measuring the faint chemical fingerprint of a planet 124 light years away by watching how starlight filters through a sliver of its atmosphere during a transit that lasts a few hours is one of the hardest measurements in all of observational astronomy. Small differences in how you process that light, what molecules you allow your model to consider, and how you account for instrumental noise can shift a headline-making 3 sigma claim down to statistical background noise. That's not a flaw in the scientific method. That is the scientific method, working exactly as designed, just on a timeline far slower than a viral headline. So where does that leave K2-18b, and where does it leave the question this video's title is built around? It leaves us with a planet that remains one of the single most interesting, most closely watched targets in the entire search for life beyond. Earth, a genuine, confirmed Hycean candidate world with a thick, water-rich atmosphere sitting in its star's habitable zone. What it does not leave us with is a confirmed detection of life, and it certainly does not leave us with a fully habitable planet. A phrase that, frankly, oversells even the most optimistic reading of any paper published on this world. The real story isn't smaller because of that. It's arguably bigger, because it's a live, ongoing scientific process happening in real time, one you can actually watch unfold paper by paper, and that process isn't finished. There's a reason Webb keeps going back to this planet, and there's a reason the scientists on every side of this disagreement all agree on exactly one thing. We need more data. That's exactly where we're headed next. Let's talk about why, despite all of that scientific walking back, K2-18b still refuses to leave the short list of the most important planets ever found. Because strip away the dimethyl sulfide controversy entirely, and you're still left with a world that genuinely challenges what habitable is even supposed to mean. K2-18b sits inside its star's habitable zone, the band of orbital distance where a planet could plausibly maintain liquid water on or beneath its surface, and multiple independent Webb observations, the ones that everyone agrees on, confirm it has a real, substantial atmosphere containing water vapor and methane, with that atmosphere potentially comprising as much as half the planet's total mass. That's not a small, thin envelope like Earth's. It's a thick, hydrogen-rich shroud that behaves less like weather and more like a planetary regulator, redistributing heat from its star across the entire globe, including into the tidally locked hemisphere that never sees daylight at all. Under Niku Madhusudan's Hycean world model, the theoretical framework that made this planet famous years before any biosignature debate began, that atmosphere could sit atop a single uninterrupted global ocean, hundreds of miles deep, under pressure so extreme that water itself behaves in ways it never does on Earth's surface. There's also a detail about K2-18b's star that deserves more attention than it usually gets because it changes the entire conversation about time. K2-18b orbits a red dwarf, a class of star that burns its hydrogen fuel far more slowly and steadily than our own sun. Where a sun-like star has a stable lifespan measured in the billions of years, red dwarfs can sustain a steady output for trillions of years, an almost incomprehensible span compared to our own solar system's roughly 10 billion year total lifetime. That matters enormously for any conversation about life. Because if a planet like K2-18b did develop the chemical conditions for biology at some point in its history, it would have had an extraordinarily long, extraordinarily stable window in which that biology could develop, without the kind of catastrophic resets, extinction-level asteroid impacts, or runaway climate shifts that have repeatedly reshaped Earth's own biosphere. That's not evidence of life. It's a description of favorable conditions, the kind of environment astrobiologists specifically look for when deciding which of the thousands of known exoplanets deserve the very limited, very expensive observing time on an instrument like Webb. And that limited observing time is really the crux of why this story isn't over. Webb is an extraordinary instrument, but it's also an incredibly busy one, shared across the entire global astronomy community, with every hour of observing time allocated, competitively, sometimes years in advance. Measuring a biosignature candidate at the level of precision needed to reach 5 sigma confidence requires stacking many separate transit observations on top of each other, each one capturing a tiny sliver of starlight filtered through the planet's atmosphere as it passes in front of its star. K2-18b's orbital period is short enough, under 33 days, that transits happen relatively often, but each individual transit only lasts a few hours, and atmospheric signals this faint require dozens of these observations, carefully combined, to separate a real chemical signature from instrumental noise and stellar activity. That's precisely why the DMS confidence level has bounced between roughly 2 and 3 sigma across every paper published so far. Nobody has yet collected enough clean data to settle the question definitively in either direction, and every scientist involved in this debate, on every side of it, agrees that more observations are the only way forward. That's also why this story isn't actually finished, and why the next chapter might arrive sooner than you'd expect. Webb's own observing schedule includes continued monitoring of K2-18b, and the scientific community broadly agrees that resolving this question properly may take not just more Webb time, but entirely new instruments built specifically for this kind of work. NASA's planned Habitable Worlds Observatory, a next-generation space telescope still in its early design phase, is being built with direct imaging of Earth-like exoplanets and their atmospheres as one of its core scientific goals, a capability that would let astronomers study worlds like K2-18b with a level of precision Webb, powerful as it is, simply wasn't designed to reach. Europe's aerial mission, an atmosphere-focused exoplanet telescope expected to launch later this decade, is being built specifically to survey the chemical composition of hundreds of exoplanet atmospheres in bulk, which could provide crucial context by showing whether molecules like dimethyl sulfide show up on other similar Hycean candidate worlds, or whether K2-18b's tentative signal really is a statistical fluke unique to one difficult dataset. So here's the honest scientific position as of where the data actually stands right now. K2-18b remains a legitimately extraordinary planet, water-rich, potentially ocean-covered, sitting in its star's habitable zone around a star that could support stable conditions for longer than our own sun will exist. What it is not, based on the full body of independent, Peer-reviewed reanalysis published between 2025 and early 2026 is a confirmed detection of life, or a fully habitable world in any sense that would satisfy the rigorous standard science actually demands before making that claim. The gap between those two statements, extraordinary candidate worth years of continued study and confirmed alien biosphere, is exactly the gap that turned an honest, careful scientific announcement into a viral myth. And understanding that gap tells you something important, not just about this one planet, but about how to read literally every biosignature headline that's going to come out of Webb and its successors for the next decade. That's exactly where we're going to land this. So let's close with the question this video's title actually asks, and let's answer it as honestly as the data allows. Has the James Webb Space Telescope detected a fully habitable planet? No. Not K2-18b, not yet, and not based on anything published through the science community's own rigorous standards as of today. What Webb has done is something arguably more valuable than a single, dramatic headline, even if it's less satisfying to a thumbnail. It has identified, characterized, and repeatedly reobserved one of the most promising, most atmospherically rich, most theoretically compelling candidate worlds ever found outside our solar system. And it has done so in a way that's forced the entire scientific community to publicly, transparently test and retest its own most exciting claim about that world. That process, uncomfortable as it's been for the researchers whose original 3 Sigma announcement got walked back paper after paper, is exactly what makes this kind of science trustworthy in the first place. A field that only ever confirms its own headlines isn't doing science, it's doing marketing. It's worth sitting with how fast this particular story moved, because it's a useful case study for literally every space headline you'll see going forward. April 2025. A genuinely careful, appropriately hedged scientific paper reports a 3 Sigma hint of a potential biosignature. Within days, global headlines strip out every hedge and announce, in effect, that alien life has been found. Within months, independent teams led by Taylor, Luque, and Wellbanks, plus a NASA-led reanalysis, systematically test that claim against the full dataset and against a much wider range of possible explanations. By January 2026, the most recent, most thorough analysis characterizes the original detection as, in the researchers' own words, a false alarm. That entire arc, from my announcement to correction, took less than a year, which is actually fast by the standards of observational astronomy. But the correction traveled a fraction as far as the original headline did, which is the real pattern worth noticing here, and it's not unique to this planet. It's the pattern behind nearly every astronomers may have found signs of alien life story you'll ever see, going all the way back to the Viking Mars landers in the 1970s and the ALH 84001 Martian meteorite controversy in the 1990s. The exciting version travels fast and far. The careful, correct version travels slow and quiet. None of this should discourage you from caring about K2-18b or about the broader search for life beyond Earth, because the underlying science here is genuinely thrilling, even without an overstated conclusion bolted onto it. We are, right now, in the first era in human history where we have an instrument capable of directly measuring the chemical composition of an atmosphere on a planet orbiting another star entirely, 124 light years away, using nothing but the starlight that filters through it during a transit lasting a few hours. That capability didn't exist in any meaningful form before Webb launched in December 2021. The fact that we're now having rigorous, peer-reviewed, statistically sophisticated arguments about whether a specific molecule shows up in that atmosphere at 2.7 sigma or 3 sigma or not at all, that argument itself is the scientific achievement. 20 years ago, we couldn't have this conversation about this planet at all. Today, multiple independent research teams can pull the same public data and fight it out rigorously in peer-reviewed journals until something closer to the truth survives the process. That's not a disappointing ending to this story. That's the actual point of how good science is supposed to work, and it's worth more than a single viral claim that turns out not to hold up. Looking forward, the honest timeline is this. Webb will almost certainly keep collecting more transit data on K2-18b because it remains, even after the DMS controversy, one of the single best Hicean world candidates known to exist. Whether that additional data eventually pushes the DMS signal up to the 5 sigma threshold that would count as a real, defensible discovery, or whether it continues to dissolve the way it has across the last 3 reanalyses, genuinely isn't something anyone can predict yet, and any video, article, or channel that tells you otherwise, with total confidence, is selling you certainty science doesn't currently have. What we can say is that new instruments purpose-built for exactly this question, from NASA's planned Habitable Worlds Observatory to Europe's upcoming Ariel mission, are specifically designed to settle exactly the kind of ambiguity K2-18b has exposed And within the coming years, we may finally get data precise enough to answer this properly, one way or the other. So here's the question worth taking with you. Given how fast an appropriately careful, heavily hedged 3 sigma scientific hint turned into a worldwide claim of confirmed alien life, and how quietly the correction traveled by comparison, how much of what you currently believe about space or about any other fast-moving scientific headline is actually the peer-reviewed result, and how much is just the most exciting version of it that happened to go viral first. Drop your thoughts in the comments. I genuinely like to know how you're thinking about this. And if you want the real, fact-checked version of the next big space headline before the exaggerated version reaches you, make sure you're subscribed, because K218b isn't finished giving up its secrets, and neither is this story.